So probably we can start. I see that there are many people. I was a bit unsure after yesterday, actually, but very good. Welcome to the last day, and this day we will start with another keynote. And I'm very sure that the keynote will be very entertaining, and then we need that after yesterday, I think. So I'm very glad to introduce Sam Malek. He's professor, associate professor in University of California. And I know Sam Malek work in different communities, in the community of software architecture, of adaptive systems, and now he's working also from several years on security. And the talk of today is about security in Android, taking the perspective of software architecture. And then I think you will explain much better than me.
Thank you very much. It's a pleasure and my privilege to be here. Can everybody hear me fine? Okay, good. I'll talk about Android security today, and I'll adopt the software architectural perspective in doing so. The talk essentially has three components. I will first try to demonstrate how software architecture has played a key role in propelling Android to become the dominant mobile platform. I will then tell you about some of the missteps in the way the architectural principles have been realized in the Android framework, which has led into the platform having a whole host of security issues. And then in the second sort of the half of the talk, it will be a little bit more narcissistic. I will talk about a couple of projects that I've led in my group for the past 5 years or so, where we've tried to adopt architecture-based approaches to analyzing Android applications for a lot of the security issues that I will talk about. Let me start off by sort of stating the obvious for probably most of you in this community. Since 2014, at least, there are more smartphones out there than there are desktops and sort of traditional servers, traditional computing devices. As of a few months ago, the majority of the internet traffic is in fact driven by mobile devices. So majority of internet usage is actually internet traffic usage is driven by mobile devices. And a lot of companies are taking notice of this, so they're shifting their strategies, they're shifting their focus towards this sector because that's where the revenues are going to be. And so it's fair to say that mobile computing has moved from the fringes of computing to become the centerpiece and the core of what it means to do computing. And for us software engineers and software architects in this room, it requires us to maybe reflect on this, reflect on the analysis, reflect on techniques and tools that we have, and see whether they're applicable to this emerging domain. The majority of the software that we develop are going to be running in these kinds of domains. But the changes that have come about by smartphones are not limited to computing. I think a technological change is real when it really changes the way we live our lives. So there have been profound impacts by sort of the emergence of the smartphones, and so humans have lived their life for thousands of years. We've gone through thousands of years of evolution, and we got by through two methods of movement. There was walking and running, and now a lot of campuses and public spaces are specifying a new mode of movement, text walking, where the zombies can sort of have their own area where they can walk around. You no longer just eat your food, you first take a picture of your food and you post it on Instagram, so the etiquettes of eating have changed. And if you're at a bad table at a banquet, you don't necessarily have to converse with others. You can just kind of tune off and go on your device and talk to people on the cloud. This doesn't happen in this conference, in other conferences. But smartphones were not always so exciting. So if you go back to early 2000s, that's about the time when I was a graduate student. And we were doing some software architectural work for mobile devices. They were quite boring devices, highly rigid systems, clunky user interfaces. And from a software engineering standpoint, it was really primitive. You had to hack your software in low-level languages, C code, and everything was really statically compiled to each other. Not a lot of customization possible. These devices essentially were useless. There was a lot of excitement about them, but there was a lot of excitement about the potential of these devices, but they were really, for the most part, not that useful. And so in a matter of, and I'm talking about the early 2000s, where you had iPads and things of that nature, In a matter of few years, we went from these completely useless devices, or somewhat completely useless devices, to having smartphones, where they have become an integrated part of our daily life. They've really profoundly changed changed the way we live. So it's interesting to go and take a look at what were the challenges that had to be overcome in a very short period of time to be able to have such a technological leap, essentially. And there's been challenges all over on the networking side, on the hardware side. I contend that there's been challenges on the software engineering side to be able to arrive at what we now know as a modern smartphone devices. And so I think about these challenges as drivers, what had to drive the community to address these issues. And so the first challenge that had to be overcome is that these devices, to be useful, you had to open these platforms. You had to open up these platforms to enable their extension, to enable entrepreneurs, to high school kids, to college students, people with potentially not a professional programming background, to be able to create creative solutions, creative ways of using these applications, which eventually the opening of the platform led to the notion of app ecosystems, where you have all sorts of creative ways in which these devices can be used for various kinds of purposes. Now, to be able to have a vibrant app ecosystem from a software engineering perspective, you can't draw on professional embedded software developers. You can't develop this software in low-level languages. You have to provide proper abstractions, proper development frameworks to allow you to, as a platform, to draw on a large pool of developers. And so you have to provide the right development paradigms for improving developer productivity to be able to have a lot of apps. And of course, having a lot of apps is very important for the usefulness of these platforms. And you have to worry about interoperability. Interoperability is a challenge if you're going to open up a platform, especially in something like Android, where it's fragmented environment, fragmented devices, interoperability of apps on different devices, but also you want to provide a rich user interface where apps can integrate and work with each other effectively. So interoperability is something that you have to address. And one of the most important challenges, which is really the focus of my talk today, is the security and privacy issues. Many of you are familiar with the security challenges of mobile code. So in the app domain, the security implications are huge, right? Because you're downloading apps with unknown provenance onto your device. You're allowing this code to execute on your device, have access to all the resources. And the way I like to think about a smartphone device is really just a bag of sensors that is always on, is always with me. I like to joke around and say my phone knows more about me than my wife knows about me, because my phone is with me all the time, right? So if you can actually hack into a mobile device, the security implications of it are much worse potentially than hacking to somebody's desktop or laptop, because you can get a lot more access to private information. So security and privacy issues had to be an issue that had to be addressed if you're going to open up the platform. And the fifth issue, which has always been sort of like ever-present challenge in this domain, has been resource constraints, battery issues, memory, CPU, and so on. And so I believe software architecture has played a key role in the sort of the early 2000s to like 2007 or so, when iPhone and Android essentially came to exist. Specifically, this notion of domain-specific software architecture and support for implementation of applications in domain-specific software architecture in a framework, in a platform, such as Android software development framework, has played a crucial role in addressing these challenges. And I'll try to at least give you some pointers as to why I think that is the case. And I'll focus mostly on Android because Android is the platform that has adopted these architectural principles more so than any other platform, and it is the dominant platform out there right now with 80% of the market share. If you look at the way you develop an Android application, for this community, I think you'll find something that is very familiar with us, because this community has advocated this idea of architecture-based development, which basically is this idea that we like to think about our systems in terms of components and connectors and so on, these architectural abstractions. It's useful to have programming level abstractions at a higher level than the typical programming language constructs of classes, variables, and so on, that more closely mimic the way we like to conceptualize our systems. So essentially providing higher level abstractions, architectural abstractions in code. So it makes it easier to codify our designs. And Android is you could say is an advocate of this model. A lot of these ideas that essentially has been developed in this community have found a home. So you have a set of component types. So if you're building an Android application, you're forced to fit in your logic into one of these predefined component types. Activities that are representations of the user interfaces, so user interfaces become activities. Services that are abstractions of programs that are running in the background. Content providers that are abstractions of the data and information. Broadcast receivers that enable components to engage in kind of a message-based publish subscribe model of interaction. And then you also will find a lot of connectors that enable the components to talk to each other. Specifically, Android advocates this notion of message-based communication. Again, something that a lot of people in this community have been an advocate of because it results in systems that are just more flexible. And Android gives you an intent messages, which are essentially the events that you would use to communicate. And it also provides you with lots of other types of connectors. So if you look inside of an Android application, what you will find is a bunch of components that are talking to each other by sending these messages. It looks pretty elegant from an architectural perspective. Very different, at least from what you would see in the early 2000s in this domain. And the platform also allows applications to talk to each other. So this is very interesting because I can have apps that are developed by one company, another app developed by another entity completely unaware of each other, yet they can somehow magically integrate and work with each other effectively at runtime. So pretty cool stuff from an architectural perspective. You dig in a little bit deeper, you'll find some additional things that resembles ideas that have been developed in this community. Each app comes with a manifest file. This manifest file essentially is an XML document. It really is a partial specification of your system's architecture, your app's architecture. It has information like app permissions. It has somewhat of a partial specification of your components. So this is a specification of an activity component, a specification of a service component. So a typical manifest file is much larger than this. And the way this is used, which by the way, as many of you may notice, it starts to look kind of like some of the ADLs that our community has developed over the past years. It's not necessarily an ADL, but it's at least somewhat resembles an ADL. And it effectively is used like an ADL. So the Android runtime environment, in fact, uses manifest file to manage the application. So manifest file is a way the application gives information about the architecture of the application to the platform. And the platform uses it for management. And then you dig in a little bit deeper into the platform, you'll find some additional elegant architectural solutions. So you find, one of my favorites is this notion of a component lifecycle. Okay, so component lifecycle is similar to the notion of components that have different modes of operation. Again, people within this community have worked on this in the past. And here's a component lifecycle for activity component. Basically what this means is that you as a developer, when you implement an activity component, you have to provide implementation of some callback methods. These callback methods are then called by the framework on the activity component to place your component in different modes of operation. And this is essentially one of the key ways in which Android is able to tackle the challenge of resource constraints, which we talked about. And this is very interesting, right? Because this is kind of counterintuitive. At least if you go back to late 90s, early 2000s, there were a lot of, let's say, negative potentially thoughts as to whether this idea of architecture-based development could ever work in an embedded mobile resource constraint setting, because you're providing these additional layers of abstraction and implementation, which has some level of inefficiency in code. But it actually turns out that even though it may be the case that those architectural abstractions are yet providing another layer of abstraction which is inefficient, through the flexibility that you get, you're able to actually offload components. In this case, an activity component can be offloaded when it loses focus. So these are pretty elegant architectural solutions that you'll find in the framework. And I think I believe for this community is interesting because a lot of these ideas were actually innovated or developed within this community and found a home in this platform. When I talk to folks, then I tell them that I do research in apps, and and there's an architecture there. A lot of people are sort of suspicious as to how interesting these architectures are. There's a sort of the general sentiment that an app is just a simple thing that has maybe 2 components, 3 components. And so, as an example, I'm just going to show you this K9 mail client app. It's a pretty popular app. A lot of people have on their Android devices. Looking at this, you might think, well, this might have like 2 or 3 components. But if you actually recover the architecture of this application, which I don't intend for you to fully understand, it will look something like this. It will have lots of components. These components talking to each other through different types of connectors, and you will eventually will find a heterogeneous set of architectural styles in this one single application. Okay, so and then this application actually integrates with a couple of external applications. So it integrates with your Firefox browser and some encryption library and so on. Okay, so what's the point? The point is that I think this community should study apps. The architecture of these systems are actually, or it could be actually interesting. So you'll find that a typical app actually has tens of components with lots of interesting properties. Okay, so Android, I believe, has been a poster child for an architecture-based development success story, in the sense that you look at what has happened in terms of at least in terms of the number of apps. There are more than 2.5 million apps out there. This shows that a large population of developers can in fact participate and exercise in this concept of architecture-based development. A lot of them may not have ever taken an architecture class. They may not know necessarily these notions of components and connectors, yet they're able to leverage the framework and the support that it provides to build systems that are quite interesting from an architectural perspective. So in that sense, it's kind of interesting that you have high school kids that don't even have professional programming background. They don't know anything about architecture, yet they're developing these systems that have a lot of architectural decisions and considerations in them. Okay, so all right, so this is sort of the first part where I really wanted to press upon you that architecture has played an interesting role in Android, but it's not all that rosy. Specifically, one issue that is facing the platform is the notion of security issues. Okay, so even though Android has been a huge success, it's sort of the newest kid on the block, right? So Android come to exist after iPhone. It is the newest mobile platform actually, right? So it is after Windows. It come to exist after all these platforms. Yet it has close to it has over 80% of the market share. But more recently, it's been in the news for bad reasons, and it's starting to sort of erode the market share because it's starting to gain a sort of name for being the sort of the mobile platform that is insecure. It's having security problems basically. And so if you look at the number of unique Android malwares from 2015 to 2016, you see a growth of over 300% in just the number of unique malwares that are targeting the platform. So these are alarming numbers, and there are potentially a lot of reasons for this. I mean, part of the reason why the attackers are targeting the platform is possibly because this is the dominant platform. So just like Windows is sort of the dominant platform in desktops, so you'll have attackers that will go after the dominant platform. But I contend that some of the security issues actually have to do with the architectural missteps in the way Android realizes architecture-based development, and I'll try to show you some of those missteps. The first issue with the way Android does things is this notion of an overprivileged resource access. So imagine you have an Android system. And by an Android system, I really mean just a device. So imagine you have an Android system and you have two apps on this device. Apps can ask for permissions, okay? And let's say app asks for permissions and an app has 50 components. Well, what happens is that all components in that app are going to, by default, by the rules of Android, are going to be granted that permission, okay? So this essentially is a systematic violation of least privilege principle, because if I only have a couple of components that need access to this permission, there is no reason to grant that permission, this resource access permission, access to APIs and libraries and sensors to all the components on the device, okay? Another issue is that in the manifest file, which is kind of partial specification architecture, it's actually underspecified. At least it's underspecified for security analysis, both for manual analysis, but also for analysis that the platform can do. And the way you can see that is by looking at the intent filter. So this essentially is an activity component being specified here. And here's an intent filter. So an intent filter is the way Android specifies a provided interface. Okay, so it's a filter on an intent. So it's kind of like you specify some conditions that match against intents. So here we have a component, an activity component, specifying a provided interface. Okay, but the platform does not provide a way for components to specify the required interfaces. So by just looking at this manifest file, you can only determine what are the provided interfaces of components and not the required interfaces, so you cannot actually connect the components together. Because if you think about a connection between two components, it requires a source and destination. The manifest file only tells you about the destinations and not the sources. Okay. So it makes it very difficult to do a security analysis because you don't exactly know what components talk to each other. You don't know it until runtime. And the second issue, which is beyond me, is that provided interfaces by default in Android are public. Okay, so you as a developer have to take extra steps to make your provided interfaces private. Okay, and every time every time a framework depends on the developers to do something properly, you could be assured that those high school kids and non-professional software engineers, or even software engineers that are not aware of the security issues, are going to just go by the default setup, and you're going to have a lot of popular applications out there where they have these exposed public interfaces because the developer just did not make those interfaces private. So as a result, what you're going to see is an overprivileged, not only an overprivileged resource access, you're also going to see an overprivileged intercomponent communication. So going back to our Android system example, according to rules of Android, components within an application can all talk to each other. Okay, so this may not necessarily have a huge security implication because supposedly all components within an app have the same level of trust, but it just is not a really great design choice to have this kind of all components can talk to each other. You want to have some kind of a structure on these interactions. But what is very important from a security standpoint is that potentially a lot of these interfaces could be public because developers are just not careful, and then you're going to have this kind of a spaghetti of possible intercomponent communications. At least components have the privileges of initiating these kinds of interactions, and the platform does not provide a way of systematically limiting what interactions are possible in the system. Okay, so these are just a subset of actually the design issues that you will find in the way Android realizes this notion of architecture-based development, and this has led into a whole host of security issues that a lot of people outside of this community would probably not realize they're architectural in nature. So if you go to security conferences, you know, they don't necessarily realize that the root cause of a lot of these security issues are in fact architectural. And they've resulted in what are known as intercomponent communication attacks. There's a whole host of them. I can spend the rest of today's presentation going through all of these, so I won't. I will just give you a couple of examples to give you an idea of the kinds of issues that you will encounter. So let me tell you about app collusion. So app collusion is pretty simple. You have 2 or more malicious applications, each of which has certain privileges that by themselves look pretty benign. So I have an application here that is requesting GPS permission. That by itself doesn't seem like it can do anything harmful. I have another malicious application that has internet permission. That by itself doesn't, again, seem that harmful because it doesn't have any private information. But there is nothing in the platform that prevents these malicious applications to actually collude and collaborate, have some kind of a covert channel behind the scene to eavesdrop on a user's location. Okay, and a lot of times the way these 2 malicious applications get on the same device is that you install, as a user, you install the flashlight app that somehow requires your GPS information, and that app starts to advertise, try to incentivize and advertise for the user to download the other applications, so increase the chances of these malicious applications getting on the same device. So that's app collusion. Another one that I'm going to tell you about is privilege escalation attack, and there are references here that you can go and find more details about these other attacks. So in privilege escalation attack, you have a vulnerable application and you have a malicious application. The vulnerable application has certain permissions that are dangerous. So the phone activity component, in this case of the victim app, has the permission to access your phone resources and maybe make phone calls or send text messages and so on. And is providing an interface that is public, that is not protected. So a malicious application, in this case the caller activity component, creates an intent, sends an intent to this phone activity component, which eventually leads to maybe sending a text message or making a phone call, thereby allowing the malicious application to escalate its privileges by indirectly going through a component or another application that actually has the permissions. So the platform gives the developer the ability to prevent these kinds of security issues. So the developer, an educated developer would actually have to, once the intent is received, the developer actually has to see if the sender of the intent has the proper permission before making a sensitive API call. Okay, so again, this is a situation where the framework provides the right mechanisms to protect these applications, but it requires developers to take extra steps to do so. And again, anytime you rely on developers to put this proper guard, you'll find lots of applications where those guards are missing, and so you'll actually find security holes in lots of popular apps out there. Okay. So how can we go address these security problems in Android? And so that's been a problem we've been looking at for the past 5 years or so in my group. And there are generally two solutions about this. You could either accept Android as is, and there's a good reason to do that because the genie is kind of out of the bottle right now. So it's kind of easier to just accept it the way it is and live with it, which basically means that we're going to try to build tools that will detect these security issues and try to protect the devices. Or we can try to change Android. And when we change Android, we have to be careful, right? Because we can't make just arbitrary changes. It's a platform that is popular, it's out there, it has 80% of the market share, so you have to be really careful about what kind of changes you make. And so if we can make changes to Android, then we can try to more proactively prevent some of these security issues by changing the way the Android works. So I'll talk about both of these. I'll give you an overview of projects that I've looked at both of these. So first, let's look at what we can do if we accept Android as is and try to provide tools that will detect these security issues. When we first came to this problem, I thought this is going to be an easy problem to solve. We have expertise in static program analysis in the group. So static program analysis basically means that you take a piece of software and you can analyze it without executing it, right? So it's a form of analyzing programs. And so we thought, well, we can just take a bunch of these apps that are installed on a device. We can treat them as one large program, one large combined app. We built static program analysis techniques that, given that combined app, we'll try to look for vulnerability instances. This doesn't seem that difficult. We've kind of gone through the difficult part of identifying these vulnerability patterns, so finding this should not be that difficult. This turned out to not be a proper approach. It turned out to be a naive approach because if you think about it, on a device you will not have 2 or 3 applications. You're probably going to have hundreds of applications, at least 50 applications, 100 applications. So if you're trying to do a very precise form of static program analysis, it's going to have scalability issues because static program analyses tend to end up becoming very similar to kind of they end up having a state-based kind of a representation. And so if you have lots of applications, and as I showed you, these applications can all talk to each other, you're going to have a state explosion problem. So if you're trying to do a very precise form of static analysis that does not have a lot of false positives, it could actually take days to do that analysis on a typical device. So then, and then the second issue, of course, is that once you do that analysis, as soon as an app is updated, and these apps get updated completely unsynchronized from each other, so every time an app gets updated, new app gets installed, any change in the configuration, you have to perform this complicated analysis all over again. Okay, so this was not a good solution. We had to go back to the whiteboard, and we asked ourselves, well, what do we need to have in terms of a solution? So we want the analysis to be scalable, of course, and we want it to be compositional. All right, and compositionality is kind of related to scalability, of course. What that means is that we want to be able to analyze each application in isolation, infer some security properties about it, and then be able to then somehow take those security facts taken from each of those apps to be able to make a statement about the overall security posture of an Android system. And the thing that helped us to do so is, again, the notion of architecture. So we realized that security vulnerabilities in these platforms are in fact architectural in nature. So why don't we try to lift the analysis from code to the software architecture level? Okay, so we decided to actually adopt an architectural based analysis perspective. And this led to a tool called Covert, which stands for Compositional Analysis of Inter-Application Vulnerabilities. And so Covert essentially is really a marriage of 3 subdisciplines of software engineering: software architecture, program analysis, and model checking. The tool basically uses 3 types of specifications, okay, which are then used by a formal analyzer for finding vulnerability instances. And so what I'll do is I'll give you an overview of what these specifications look like. So our approach is alloy-based. We model these specifications in Alloy, which is a formal specification language. Here's what an Alloy specification of Android looks like. I don't intend for you to understand these Alloy models. I'm just showing it to you so you can understand get an idea of what the Alloy models look like. So this in fact is a very small subset of a specification or codification of what it means to be Android. What it means to be an Android architectural style in Alloy. So essentially this Alloy representation is like almost like a formal way of specifying the architectural style of Android. What are the component types? What are the connector types? What are the restrictions between the way these components can talk to each other and so on? So this allows us to give the model checker the knowledge that it needs about what Android applications are and how they work. Okay, so it codifies essentially the Android's architectural style. And this, of course, is something that we built manually through several weeks of effort. It's hundreds of lines of a specification. It's something that the user of the tool doesn't have to see. It's sort of behind the scene. It doesn't change because Android architectural style doesn't really change. Okay, so the second component is the specifications that we extract from the apps. And so we have program analyses that extract architectural specifications for apps per application. Okay, so and then they present them in Alloy. So I'll try to give you an overview of how this works. So the static extraction of architecture from application relies on static program analysis. It has 4 steps. In the 4 steps, we extract some components and we extract all the information essentially about the architecture that is available in the manifest file. So these are components, provide interfaces, permissions, and so on. We then extract additional information from the app's bytecode. So our techniques actually work off of the bytecodes. It doesn't require the source code. So we'll find places where intents, for example, are instantiated. We might find some additional intent filters that are specified in code. So we extract all that stuff from the bytecode. Essentially, it's an architectural recovery technique, if you will. We then obtain an event-driven behavioral model of each component. And this basically is a model of the component's basically behavior in terms of its interfaces. So for example, we might find that when a particular button is clicked, a particular intent is instantiated and sent by a component. We can identify that when a particular provider interface is called, these are the API calls that happen in the component. And then the fourth analysis that we do is that we try to look for sensitive paths, and these are security sensitive paths. So for example, in the case of victim application in the privilege escalation attack, we might find that node F here is an API call that is permission protected, so maybe sending of a text message happens here. We do a backward control flow analysis in the case of privilege escalation attack to figure out if this particular permission protected API call is in fact reachable from the provided interfaces of the component. For other kinds of vulnerabilities, you may want to do a different kind of analysis. So you might do information flow analysis or data flow analysis for information leakage and so on. And given all this, given this extracted architecture of the application automatically through program analysis from each app, we represent them in terms of separate Alloy specifications. So you might have an Alloy specification for the malicious app. You will have an Alloy specification for the victim app. And what is nice here is that this approach by default is compositional, because if one of these applications gets modified, we can extract the corresponding Alloy specification independent of other applications. So we don't have to perform the analysis all over again for all the apps. And then the third type of a specification that we need are the vulnerability assertions. So these are properties that we're interested in checking in our extracted architectural specifications. So an example of a privilege escalation assertion is shown here. Again, I don't need you to understand what these Alloy models say right now, just to kind of give you an idea of what these assertions look like. So these are, again, specifications that we have built. So we have a catalog of these vulnerability patterns that, that we can essentially check for in our architectural in the architectural specifications that we have extracted. So given these 3 sets of specifications, we feed them into Alloy Analyzer, which is a model checking tool essentially. And the Alloy Analyzer essentially tries to use a SAT solver to solve for this formula. So basically what we give to an Alloy Analyzer is an Android specification S, a set of architectural specifications for apps M, 1 or more vulnerability assertions P, and then Alloy Analyzer uses a SAT solver to see whether model specification M satisfies S and not P. Okay, so if it satisfies S and not P, you know the system is secure. Otherwise, you know there's a vulnerability, and then the model checking tool, Alloy Analyzer, will produce a counterexample that shows where exactly the security issue is. This, in this particular case, ends up looking like an essentially path between your components. Okay, so this essentially tool will detect that there's some kind of a security issue that is possible there. And of course, the space could be pretty large, right? Because you don't necessarily have 2 victim applications. You might have, 50 or 100 applications, and so the search space could actually be quite large. We've done lots of experiments with the tool. In one set of experiments, we downloaded 4,000 apps from 4 different repositories, including the 1,000 most popular apps on Google Play, and also some malware samples that we were able to get our hands on. And we constructed 80 non-overlapping bundles of 50 apps each. So basically, this allowed us to almost like do 80 independent experiments, where each experiment corresponds to a device with 50 applications on it. Just sort of randomly selected, just making sure that the apps don't overlap. And we wanted to see, well, is Covert really able to find real security issues if we were to use it on these devices? And so we found that Covert detected 385 security vulnerabilities of different type, and 36 of them, for example, were privilege escalation attacks that I showed you earlier. Then we manually investigated these attacks, and we saw that there was 61% true positive by the tool. So out of every 2 warnings that comes out of a tool, one of them is a real security issue that you want to fix and you care about, basically. So those are actually pretty decent results for a security analysis tool. So there were a lot of previously unknown security vulnerabilities that we found, and we try not to disclose them. We try to kind of follow ethical disclosure of security vulnerabilities. Just to give you an idea, here's one of them. Just to kind of give you a perspective into the severity of some security issues. So this is a barcode scanner app, and what that means is that it allows you to make invoice payments using SMS. So you essentially scan the barcode on an invoice, and then you use an SMS to pay for the invoice through your bank. So this is a real application, real security issue. It provided an unprotected intent filter that allowed another application and another malicious application on the same device to essentially make unauthorized payments through this vulnerability. So it's an example of a security vulnerability that there's in fact an incentive for an attacker to try to exploit. This shows you a comparison of covert with some of the alternative tools out there. So these are the alternative tools that don't leverage architectural knowledge. So as I said, in covert we raise the level of analysis to architectures. And so you can see that covert actually more or less has a linear growth, whereas Almondroid and Ditfell, which are the competing tools that are pure static analysis techniques, can't really run beyond 8 components or 30 components or so. So the tools just stop functioning after those many components, just because the scale of the problem grows non-linearly. Okay, so this was good. We actually have, so there are a couple of government agencies that had funded the work and are actually using this tool on a daily basis to protect devices of their employees and so on, or at least that's what they tell me. So that part was good, except that we realized that over time, the malware authors have become more creative. So what they do is that to prevent detection by static analysis tools, what a lot of malware authors do is that they try to hide their code. Okay, and there are multiple techniques you can adopt for hiding your code. One of them is you can try to take the malicious part that actually, for example, creates an intent here. You can try to make that to be dynamically loaded code. So the platform actually allows you to dynamically load code at a later point in time. So at the random point in time, maybe on a Friday night, 3 in the morning, the application downloads some malicious code. And that since that code does not exist when we run covert or any other kind of static program analysis based approach, you won't be able to detect it. Another approach that is used is that attackers try to encrypt the code. They try to encrypt the code that actually does something malicious. So it makes it very difficult for static analysis tools to static analyze them. So because of these, at the end of the day, covert as well as pretty much any other static analysis based detection approach cannot detect these security issues where the attacker is smart enough to hide the code. Right, and so this basically brings us to the next part of the talk, which is, well, there's only so much you can do without changing Android. Okay, so without changing Android, you're going to be able to take a whole host of issues, but if the attacker is stealthy, they can try to hide the code, which basically means that you won't be able to actually detect it in these Android applications. So we said, well, at the end of the day, it looks like we probably have to make some changes to the Android. And the question is, well, what kind of a change can we make to Android that would be acceptable? Because, as I said, the genie's out of the bottle. It's a platform that is out there. It's very popular. And so there are 2 criteria that you have to consider. One is usability, right? So we can always come up with a different version of Android that is just not usable, like changing the way the permissions work. So the user grants permissions to components individually, but if the users already don't know what they're doing when they're granting permissions to applications, what are they going to know about granting permissions to components? So that's just not a usable solution. So you have to worry about usability, and usability and security are always kind of like 2 sides of the same coin, basically. The second issue is that whatever change you make to Android, we want to have compatibility with the existing apps, right? There are more than 2.5 million apps out there. And we don't want to create a new version of Android where all those apps stop working. So we have to remain compatible with the existing app ecosystem. And if we don't remain compatible, that essentially is a non-starter as a solution. So given this criteria, we thought about this and we realized that, well, if you're going to make one change that is going to have sort of a broad impact on all the security issues in Android, that's going to have sort of maybe the broadest impact, is to try to address the systematic violation of least least privilege principle in Android. As I say, least privilege principle in Android is the mother of all evil. And the reason for that is because if you think about like the way Android does things, it by default results in architectures that are overprivileged. So if you think about this kind of basically cloud, the sort of the light-colored cloud as the existing attack surface of an Android, if you were to actually reduce that architecture to a least privilege architecture, you'll be able to significantly reduce that attack surface, which basically means that you're able to, in one shot at least, address many of the security threats that were introduced earlier. And so then the question is, how can we develop a way of establishing least privilege architecture for these Android applications? And we realized that, well, since our approach assumes already implemented applications, and we already have implementation of these components, it seems plausible for us to be able to build static analysis tools that can analyze the implementation of each component and determine exactly what are the privileges that that component needs to have for it to function properly and nothing more. Okay, so it seemed plausible to be able to do this. And that's exactly what we did. So going back to our earlier example, what we could do is that, so this shows you the way Android apps are overprivileged in terms of resource access. What we could do is we could actually analyze each of these components implementation and figure out if any of these components are actually making API calls, so maybe get GPS and send text message. Are they making actually Android API calls that require these permissions? And if they do, we grant those permissions to those components so they can continue to function. And components that don't require any API calls that require permissions, we can simply revoke their permissions. And by doing so, we're able to have these existing applications work as they were working on regular versions of Android, but without all the extra privileges. Okay, so that's sort of the key idea behind the approach. And the way we do this, of course, is that we developed a mapping of API calls to permissions. So we essentially did a mapping. We actually relied on prior work that had done a complete mapping of all the API calls in Android to the permissions that are required to use them. And so then we build a static analysis that essentially goes through the applications bytecode through the components bytecode and determines exactly what are the permissions that should be granted to the components. We did something very similar in the case of intercomponent communication. So as I showed you earlier, this figure shows you how all components can potentially talk to each other. Well, what we could do is we could analyze each component and determine what are the intents that are instantiated in each of those components and who are the intended recipients of those intents. So we can essentially figure out the required interfaces of each component by statically analyzing each component and get rid of or prevent communication possibilities between all components that don't need to talk to each other for providing their functionality. So if we do something like that, we'll end up with a much more elegant model of the system's architecture, or what is possible in terms of the architecture, where components can only talk to components that they need to talk to for providing their functionality, and they can't to talk to any other components that they don't need to talk to. Okay, so we realized this approach in a tool called Deldroid, which was actually presented earlier this week here. It stands for Determination and Enforcement of Least Privilege Architecture in Android. At a high level, the way it works is that we take a set of apps that by default are overprivileged in Android. We statically analyze them to identify the least privileged architecture using the methods that I described earlier. Essentially, if you subtract the privileges that are needed for the applications to work from all the privileges that are granted by default, you're going to figure out what are the extra privileges that are not needed by components. And then we created a custom version of Android. So you essentially would install this custom version of Android, but you can go and install any app out there in the Android world, and they would all work properly on this custom version of Android. And this custom version of Android essentially gets these extra privileges in the form of event condition actions. And then basically we implemented some simple changes to the Android framework where we monitor the resource access API calls and the ICSA calls. And so we then check them against the privileges that should be revoked, and then we essentially establish a least privilege architecture. We enforce the least privilege architecture on top of the modified version of Android that we have. So this essentially effectively mitigates this hidden code security issue that I showed you, because if that piece of code does not exist in this caller activity component, Deldroid is going to prevent that interaction from happening, and therefore you're not going to have the privilege escalation attack that I showed you earlier. Okay, so because Deldroid is only going to allow components to do what they're able to do based on the logic that is in them. So if you're going to have some dynamic loaded code that is going to get loaded later on, that code cannot do, will not have access to any other privileges than what was possible initially. So this also means that if your components already are malicious, right? If the code that you're analyzing is already malicious, then Deldroid is not going to be effective in preventing them. But then you have tools like Covert that can detect them. So if you use Covert together with something like Deldroid, then you're addressing both sets of security issues. So we wanted to see how much can we actually reduce the attack surface of Android systems using this approach. We did 10 experiments with 30 randomly selected apps from a collection of apps that we had. So you have some details about what these apps are and their statistics. We then compared the reduction in the ICC communication, and we got 99% reduction in ICC privileges. That just shows you how overprivileged the ICC communication is in Android. So all components can essentially talk to each other, or a lot of components can talk to each other. And so we can actually reduce it by 99% and yet have these applications execute. Okay, so that's sort of the key issue, is that if you can reduce the attack surface by 99%, this essentially means that you've reduced the effort required by a security analyst that is going to manually investigate maybe manually investigate the security property of an Android system by 99%, because if you reduce the possible flows of information and interactions by 99%, that's what it essentially comes down to. And we also reduced the resource access privileges, which are the permissions to access the resources, by 97%. So 97% to 99% reduction in privileges granted to the components. We then wanted to know, well, this is a huge reduction in attack surface, but is it really effective in actually preventing security attacks? So we used a data set of 54 malicious and vulnerable apps. And what is special about this data set is that for these sets of apps, we actually knew the way that is required to create an exploit. So we actually knew the steps that are required to be performed to be able to create a security exploit, because we needed that. We wanted to execute that on our modified version of Android. And these apps had 42 security attacks, 18 privilege escalation attack, and 24 hidden ICC attacks through dynamic class loading. So when we executed these 54 malicious apps, we tried to create the security attacks on our modified version of Android. We got 100% recall. So we actually prevented all security attacks by just reducing the attack surface. We were able to prevent all security attacks. And we got a precision of 97%. What that means is that there was one ICC that was actually benign ICC that the approach prevented. And the reason for that is because this approach relies on static analysis, which has false positives. So there was one ICC communication that should have been allowed. It was actually benign ICC that was prevented. But nevertheless, it shows like how effective the technique could be for preventing a whole host of security issues in a kind of a proactive fashion. We're not really detecting the security issue. We're just simply preventing it by reducing the attack surface of components. So to recap, I basically told you about the important role of software architecture in advancement of smartphone computing, particularly in the Android, in overcoming some of the key security issues, some of the key challenges that we talked about. I talked about how some of these architectural missteps and misconceived architectural principles are the root cause of a whole host of security issues in Android. And then I told you about, I gave you an overview of two projects, Covert and Deldroid, that try to mitigate these security issues in complementary ways. Covert tries to mitigate it by detecting the security issues without changing Android, and Deldroid tries to proactively prevent them by actually making small modifications to the way the Android platform works, yet remains compatible with the existing app ecosystem. So some of the broader takeaways beyond security and beyond Android and all the stuff that I said, there's a lot of frameworks out there. And so I believe one sort of the broader takeaway you can take from this presentation is that generally designing a new framework, even a framework as successful as Android, turns out to be pretty difficult. If you make a small mistake, like some of the mistakes that we saw in the way Android is realizing this sort of the security principles, it could have huge implications. So it's paramount that if you're a developer and you're developing a new framework for web application development or whatnot, it's paramount to get it right the first time. And I don't really know if this community or software engineering community actually has proper solutions for helping us develop proper frameworks. How do you build frameworks? How do you validate the way you're building frameworks for the properties that they're going to have, right? So if there's one lesson we can take from Android and its security implications, is the fact that how some of these small design decisions you make in the design of a framework could actually have broad implications, potentially after the framework has become very successful, and at that point it's very difficult to make changes to the framework. So you're kind of stuck with what you have in the first try. If you're a developer, if you're an architect, I think selecting a framework is probably the most important architectural decision that you're going to make in the design of your architecture, because frameworks can determine so much of the architecture of your application. And so obviously if you saw with Android, I mean, pretty much like locks you into a particular set of architectural styles that you have to use. Some of the other web-based frameworks and other frameworks also have the similar properties. So as a software architect, you really want to think twice before choosing a framework. I've seen a lot of cases where people choose a framework before they figure out what the architecture is, and that's kind of like putting the putting the cart in front of the horse or whatever. And sort of the third takeaway, I think, is that so I've been sort of part of the software architecture community, and I've somewhat consistently throughout my years as a software architecture researcher, I've always been disappointed by not having data, by not actually having architectural models and data that I can actually empirically use to evaluate my research and validate my work. And I think the notion of the availability of lots of frameworks with lots of rich architectural elements and decisions in them, the availability of app ecosystems where you actually have lots of these apps at your disposal that you can analyze, and the existence of program analysis techniques that allow us to extract these architectural models from these apps, like what I showed you with Android. So in Android, you can actually, at scale, go and extract the architecture of lots and lots of applications, and you can then analyze various architectural phenomena, various empirical questions from the architectural models that you extract in this domain. So I think this really opens up the possibility for doing potentially interesting research using existing architectures in action and at scale in these emerging domains. So with that, I'd like to acknowledge the students and collaborators in various projects that have led into some of the stuff that I talked about, and I'd like to thank you for listening, and I'll be happy to answer questions.
Questions there? Do you have a microphone for that? No, probably not. For live streaming, yeah. But how to do that? Do you want mine?
I think I'm fine, right? Can you hear me there? Yeah. Thank you for the talk, it's great. I have kind of a philosophical question. So in the cover tool, what you were using is, let's say, formal semantics for the model. And you apply formal methods in a way, so model finding to verify properties on the model. In the second tool, in the build drawing, what you have is sort of an operational definition of what a problem is or a violation of a constraint is, and then you use an algorithmic approach to find it. Am I completely off?
No, I think you're right. I mean, definitely with covert. I mean, I think you nailed it with what we do in the covert. The second approach, I'm not really sure if I would say it's algorithmic. It's more of a program analysis based approach. Okay, I don't know if that's what you mean.
Just the Android ecosystem.
So I think the model checking techniques can face scalability issues potentially, because for example, Alloy Analyzer is known to potentially have scalability issues. Exactly. Though, however, in this domain, I actually think it scales relatively well because you actually have bounded, so the bounds are sort of set, and we've done. So I think when you try to do model checking in source code, it's very difficult because you might have variables where the bounds of those variables could really be large, right? And so then the tool can't scale. Because we're trying to do the analysis here at the architectural level in terms of architectural models, the bounds end up being, we end up having pretty nice bounds on various Alloy constructs that we have. So in that sense, I think it scales. But of course, in general, it has scalability issues. If you try to maybe go, I don't know, to thousands of applications, we haven't really tried to do that experiment with thousands. I mean, and also right now, you don't really have devices with thousands of applications on them, but it definitely works up to like hundreds and 200 applications. We've done some additional work. We actually had a paper last year actually, where what we've shown is that once you perform an analysis using Covert once, if there's a small change to your system, so for example, let's say I've done analysis with 100 applications, and now only one of my application changes. We don't actually have to do a model checking of the entire space again. We actually have an incremental way of doing the analysis. So that actually allows the analysis to scale a little bit better. I didn't talk about that today, but that's an important part of the work that allows us to, because eventually what we want to do is we want to do this essentially in real time, like as a user like installs a new app or an app that gets updated, we want to do the analysis almost in real time. And so what we've developed is a way of doing that in an incremental fashion. So if there's a part of the solution space that doesn't change, we don't actually have to check that. We only check the part that has changed as a result of a change in the model, if that makes any sense.
Other question? Yep.
Your combination of Covert and Delroy seems like it can prevent a lot of the security issues that you explained today. But well, us sitting here in this room, we understand what you just explained, and we'll be able to use the tools and prevent all those security issues. But at the end of the day, the people who are exposed to these issues are the end users of Android, who are mostly non-tech savvy users, including my grandma, who's 90 years old. And so, like, would you like project the future that any users of Android would be able to somehow fly these techniques and get rid of all the security issues on their phone?
That's a good question. I think we've never had the intention of these tools being used by grandmas, by end users of that nature. So it's always been intended to be used by security analysts of an organization with some amount of training. And so yeah, so we haven't really, I guess we haven't really developed these full tools for end consumers, you know, like sort of like the sort of the average person that, you know, it's been, and even the scenarios that I presented with like 50 apps on an app on a device. So let's say you're White House and you're trying to prevent Trump from using Twitter or whatever, I don't know. So you're trying to protect the apps that a president can install on his phone. Oh, that would be a very interesting application of Delroy to prevent access to Twitter. So if you're trying to like vet a set of applications for use for internal purposes by your organization, then this would be a proper tool to be used by a security analyst. We didn't think, but you're right. I mean, if eventually you want to get to a point where you can provide these kinds of feedbacks and make it available for end consumers, we really haven't got there. And I agree with you, these tools right now, in terms of the output that they produce, are probably not that useful for just complete end user of these devices.
Other questions? Yep.
So now we get a really nice talk about security in Android, but if you look at Android, there are also extensions to other devices like Android car, your smartwatch deals with Android intelligence. How does that reflect on security and privacy in general?
That's a great question. We haven't gone beyond the sort of the Android on smartphones and tablets. But you're right. I mean, one of the things that Google is trying to do is they're trying to push Android for automobiles. Essentially, they're trying to make it to be the platform of the Internet of Things, at least for a good subset of Internet of Things. And when you make it a platform of Internet of Things, then you're talking about more privacy and security issues. So now if I hack your phone, I can potentially hack your fridge, and I can hack your car, and just the implications of it are huge. And so I really don't have a good answer, but that certainly is an area that we want to explore next, is to try to get our hands on these emerging domains where Android is going to be deployed. Yeah.
There was a, yeah.
Yeah, first of all, thanks for this great talk. Don't really have a specific question, but more thought. Given the fact that some development is going towards mobile web applications as well, also with Google pushing it in the last year with the progressive web app spender, which would shift then the security issue away, a little bit away from the security issues that you were mentioning now to the browser.
Mm-hmm.
Would that be some sort of an alternative way to tackle it?
That's a good question. So I mean, it will be different, right? So it will be a little bit different. When you talk about, so this would be like a web view kind of a based kind of a component. In fact, one of the ICCs that I didn't present because I didn't have time is called fragment injection, which in fact is an ICC intercomponent communication that actually uses components that are using the WebView component, where the component is essentially is a website. It's almost like a cross-site scripting, except it's like a cross-app scripting. You know, you're familiar with cross-site scripting. So I think it would be different set of attacks, but I think security attacks will still be there, exactly right. I think maybe one benefit of it, if you move towards web applications, that maybe there are a lot of existing tools for security analysis of web applications that you might be able to reuse in that domain. But I know for a fact that a lot of WebView type of components already have some of the ICC attacks that I talked about. Yeah.
And there is, yeah.
Let's say in the Netherlands we have a big debate on, let's say, the liabilities of all the providers of technologies, the IT technologies, related to security and privacy. In other fields where goods and services are provided, the producer or the manufacturer is liable for that, or loss for that, etc. And in the software field, it has been very difficult to arrange this. But however, in the malware, there is, let's say, those people can
Exactly.
manufacture, let's say, malfunctioning functionality without any, well, let's say, penalty.
Exactly.
And so, you, let's say, in your research, do you see possibility, like, well, when you are driving a car, we have a license plate, so you can trace back when something is done with that car, and there are serial numbers on all parts. But in this malware production, could there be a kind of imposed identification of the manufacturer of that malware through
Some level of attribution of who's right.
that cannot be changed, or meaning, so whatever, such that you can always trace back to the manufacturer of the malware.
Right.
So
Right.
more the source.
Yeah.
What's your opinion on it?
I think you nailed it. So I think one of the reasons why there are a lot of security issues in this domain is that there's the consequences of you actually creating an Android app with something malicious on it, and let's say somehow you can bypass because Google does some checks. They don't do as extensive checks as, for example, iPhone does, but they do some checks. They run some automated tools, and there's been lots of cases where people have been able to get around those checks to be able to get apps on the app market, make it available to millions of users, right? The consequences are not that much, right? So if they catch your app being a malware, they just yank it off of the app store, and I mean, I'm not a legal expert, so I don't know what the legal implications are, but I don't think there are any really major legal implications, especially if the app developer cannot be really.
Addressing more can we put something in the software that they're creating? That there should be some kind of a license plate on their malware app, so that we can a software solution. There's a creator that identifies the MAC address of their server or the IP address somewhere.
Well, the malware author is not gonna comply with that. But like Google could try to. You mean like Google tried to like force app developers to do something like that? Right. To the best of my knowledge, they don't do something like that, as far as I understand. So it's, I think for as much as like $20 or $25, you can put your app on App Store and on Google Play, and until proven guilty, I guess you can have your app up there. I think it would be very interesting research. I mean, it's kind of an interesting. It's a research that is very difficult for an academic like me to do, because I think it's a proper type of research for someone like Google to do, right? Because they are operating the Google Play app market, and but I think it's a very interesting point. Some way of essentially stamping and having an approval of what the app is doing.
We are running out of time, and we'd like to thank you again
Great,
with
yeah.
a simple gift.
Thank you.
And a very simple announcement. Now there is coffee break, and after the coffee break there will be 2 parallel sessions. In this room, there will be cyber physical systems and Internet of Things. And in the other room, there will be automotive, obviously in the Tesla room. But there will be a guy from, one of the co-moderator will be from Volvo Cars. And please, after the session, come back here. You have 0 minutes to come here because there will be the award session. And then please come.